Greetings. This is the fourth in my lecture series on elementary category theory. And I wanted to, first of all, thank all of you who have left comments. I appreciate those comments. Please keep them coming. And second, I wanted to mention that the book that I wrote upon which these lectures are based has been accepted for publication. And so I will be signing a contract sometime in the not too distant future. And once I do that, the book will no longer be my property, and I will have to take down my offer to sell the PDF versions on my website. So if you're interested in getting a copy in PDF format at a price that I think will be significantly less than the price of the actual book, you might want to visit my website, www.sroman.com. For this lecture, I wanted to give you several examples of functors. But as I began to think about how I would do that, I realized that I need to back up a little bit and present a couple of topics in a little more detail than I did before. In particular, we talked about comma categories, and the simplest one was if C is a category and A is an object in the category, then the category A arrow C has for its objects the set of all the objects are pairs C morphism from A to C. I called A the anchor object. I think I did. If I didn't, I am now, just to have a term, because the anchor object doesn't change. The objects of this comma category are found by changing the codomain of the morphisms in the codomain, but they're all arrows leaving the anchor object A. So I use the term anchor object, although that's not standard terminology. Picture, here's the anchor object, one morphism and another morphism. You can identify these pairs with just the morphism, the second coordinate, because if you know the morphism, then you must know the codomain, which means you must know the first coordinate. So you can think of the objects simply as morphisms, informally. Now the question is, what are the morphisms in this comma category? Okay, so I want to define the Homme set from B, F, A to B, from this object to this object, C, G, A to C. And I'll call this set H, this Homme set. So what are these morphisms? Well, let's make another temporary definition. Let's say that a morphism alpha from B to C is qualifying for the pair B, F, A, B, comma, C, G, A, C, So I'm defining the term qualifying if, when I put this morphism alpha in the picture here, the triangle commutes. So first G, then alpha, first F, then alpha would be G. Okay, I'll write that again. Alpha circle F equals G. Okay, so now by definition then, H consists of the qualifying morphisms for the pair P. Now there's a little bit of a subtlety here, which is really kind of the reason I'm doing this in such detail. When we think of alpha as a qualifying morphism, in other words, as a morphism satisfying this property, its domain is B and its codomain is C. But when we think of alpha as a morphism in the comma category, the domain is this object and the codomain is this object. So we have two contexts in which alpha exists. Or in other words, alpha exists in two different Homme sets, and that means it's two different morphisms because the domains are different and the codomains are different. So I'm going to put a bar over the alpha when we are thinking of the morphism as having this domain and this codomain. And we'll leave the bar off when we want to think of alpha as having this domain and this codomain. The other item I want to go over is the categorical product. You might remember that in the first lecture I tried to motivate some categorical concepts by talking about the product of vector spaces, the direct product of vector spaces, and the projection maps. And we define the direct product strictly in terms of maps, so that it was, in that case then, only defined up to isomorphism, but that definition really captured the spirit of the direct product. So I want to do that now for arbitrary objects in an arbitrary category. So the formal definition of the product of two objects goes like this. C is a category. A and B are objects in C. This is going to look essentially identical to what I did for vector spaces in the first lecture. So a product is a triple. A cross B, a morphism row 1 from A cross B to A, and another morphism row 2 from A cross B into B. So this is an object in the category C, and these are morphisms in C. And it must have, this triple must have the property that if we have any other triple of similar configuration, then there exists a unique morphism theta from X to A cross B with a certain property, and I'm going to draw the picture now so you can see what's going on. Here is A cross B, projection, projection. These are called the projection maps. X, F, and G. There exists a unique morphism theta from X to A cross B with the property that this diagram commutes. So for which, so if we take theta rho 1, we get F, and we take theta rho 2, we get G. Theta is called a mediating morphism. The uniqueness is nice because sometimes if you want to show two maps are the same, if you can work out a diagram like this where the two maps both sit here, then you can use the uniqueness of the mediating morphism to conclude that the two maps are the same. Some quick examples. In set, the product of two sets is just the ordinary Cartesian product. And I will invite you to verify that. For group, vector space, as we have seen, and ring, for example, module, the categorical product is the common product that you would have seen in an abstract algebra class. Poset is kind of an interesting one. Here the categorical product is the least upper bound of two elements. So A cross B is least upper bound of A and B. That's kind of interesting. It's interesting to observe that the Cartesian product of sets, the direct product of vector spaces, and the least upper bound and poset are all the same categorical concept. So that's an example of how category theory is unifying. I should point out that categorical products don't always exist. For example, in field, it is possible that you can take two fields like Z2 and Z3, for example, and there is no product. No field will fit this definition of product, and I invite you to think about why that might be. Keep in mind that the morphisms between fields are ring maps, but they must be either the trivial map or they must be embeddings. And so that might help you as you think about that. When a category has the property that any two objects have a product, then we just say that the category has binary products. We can define the product for more than two objects, which I may do later on. It'll be quite some time before I get to categorical products. So if I last that long, we'll define the product in more general terms. But for now, this is all we need. We can use the categorical product of objects to define the product of morphisms. So let's say we have two morphisms. Sitting inside a category that has binary products. Okay. we want to define the product morphism F1 cross F2, which will map A1 cross A2. Here are the projections for that product to B1 cross B2 with its projections like that. It's common practice, although kind of sloppy, to simply write let A cross B be the product of two objects. You can't define the product without the projection maps. Obviously that's critical to the definition, but sometimes we get a little sloppy and just talk about them. It's the same thing we do for posets, for example, let P be a poset or let G be a group without saying what the order relation is or the product in the case of groups. So let's see if we can discover what this product should be using what might be considered typical categorical reasoning. So what we need is a map into a product. How do you define a map into a product? Well, if you look at the definition of categorical product, it's the mediating morphism is a map into the product. So all we need to do is produce a pair of maps from the domain into this product and then invoke the definition of product. Well, that shouldn't be a problem. In fact, I can draw a picture room. Here's B1 cross B2. And we have our projections, beta 1 to B1 and beta 2 to B2. And here is A1 cross A2. This is our domain. We need to produce maps from A1 cross A2 to B1 and to B2. But we have a projection alpha 1 into A1, and then we can use F1 to complete this side here and take us to B1. And we do the same thing on the other side. Alpha 2 goes to A2, and G then continues to B2. So these composite maps are just what we need to guarantee that there is a unique map theta for which, if we start with theta and then we follow with beta 1, we will get this composite F1 composed with alpha 1. And if we start with theta and then we follow that by beta 2, we will get the same as if we start with alpha 2 and follow that. Oops, sorry, this G is F2. F2. And because the mediating morphism is unique, we can define it to be the product F1 cross F2. So set F1 cross F2 equal to theta. Okay? So that's a typical example of definition using what you might call the mediating morphism trick. Because the mediating morphism is unique, it can be used to define maps through certain properties. Okay, so that's what I wanted to do before starting to look at some examples of functors. Examples of functors. Let me first give you a simple example of a couple of functors that map the category of commutative rings to the category of groups. So first we might define a matrix functor. So here n is a positive integer. Fn takes a ring to the general linear group, which is the group of all non-singular n by n matrices over R. Non-singular n by n matrices over R. A morphism between rings, a ring map, will get sent to the same map applied element-wise to the matrices. Element-wise. And I'll let you verify that that defines a functor. Another possibility would be a functor that takes the ring R to the group of units of R, the multiplicative group of units of R. And a morphism, a ring map, will get sent again to the same map, but restricted to the units. Because a ring map does map units to units. Here's another example, a little more unusual maybe. If P is a poset, then a down set is a subset of P with the property that if A is in S and X is less than A, then X is also in S. Okay, a down set. So when a down set is a set that when it contains an element contains everything below that element. Okay. When we're drawing pictures of posets, we sometimes draw a down set that looks kind of like that. So everything in here is part of the down set. So we can define a down set functor from poset to poset. F sends a poset P to the family of all O of P, the family of all down sets in P. And that's ordered by set inclusion. The morphisms in P, in poset, morphism from P to Q, these are the monotone maps. Now, a monotone map does not send a down set to another down set necessarily. And that's pretty easy to see if you just take something like this little poset here and you send it to this poset here and you send 2 to 2 and 1 to 1. That's a monotone map, but the image of this entire set, which is a down set here, is not a down set over on that side. On the other hand, F inverse does take down sets to down sets, and I'll let you sort that out. And so we can, our functor can send F to the inverse image on the down sets. So this would be the down sets on Q to the down sets on P. This is an O for down. Okay, so that defines a functor, and again, I'll let you check that. Okay, next example is a bit of a tongue twister. We'll start with the category C, and we will define a functor f that sends C into the category of small categories. And f takes an object A to the comma category of all arrows entering A. So that's the object portion, the object part of the functor. So it's sending an object A to the anchor object of a comma category, so it's kind of, we could maybe call it the anchor functor, just between you and me. Okay. The real issue is what happens to a morphism. Okay. So if we have a morphism f from A to A prime, that has to get sent to a morphism from the comma category C into A to the comma category C into A prime. What is a morphism between two comma categories? It's a functor. So this is a double arrow. This is a functor. So our initial functor that we're defining, capital F, sends morphisms to functors. So to define this functor, FF, we need to say what it does to objects and what it does to morphisms. So I'll draw a line here. So first of all, the object part of FF. Well, for that, FF takes an object, and what does an object look like? It looks like a pair, and this is going to go to another object, and it will be F circle alpha from C to A prime. Okay, we need to send an object here to an object here. So these objects are basically arrows from something into A, and these are arrows from something into A prime, and we can swap the codomains from A to A prime by following with F, which maps A to A prime. So it's essentially follow by F. Okay, now what about the arrow part? Of FF. So that's going to map an arrow in here to an arrow in here. So let's review again what the arrows or morphisms here look like. U bar, taking an object in CA to another object in CA. C prime, beta, C prime A. By definition of morphism, that comes from a qualifying morphism. Map a morphism from C to C prime, for which U followed by beta is equal to alpha. Remember the little picture we drew before of the triangle that has to be commutative. So that has to go under FF to a morphism in this category. Same category, but A prime instead of A, different anchor. So FF of U bar is going to take the image of this object to the image of this object. And the image of this object under F is just followed by little f. So we're looking at C, comma, little f circle alpha from C to A prime to C prime F circle beta from C prime to A prime. And this must come from a qualifying morphism. What does the qualifying morphism look like? It's a morphism V from C to C prime, V circle beta circle F is equal to F circle alpha. But if you look at this and you look at this, you will see that all we need to do is take V equal to U. So everything essentially is U except the domains and the codomains are changed appropriately. What we need to do now is to verify that FF is a functor. And once that's done, we need to verify that F is a functor. And I'm going to leave it for you because it's going to take a while for all this to sink in. And I think my advice would be, if it's not all crystal clear to you, which would surprise me, is to go over this, see if you can duplicate it yourself without looking at any video or notes. If not, then review the video and try again. And once you can reproduce this argument, the rest of it will be much easier than it would be now. And if I just continue, I think it's just going to pile more complications on top of each other, and so I'm going to leave it. Okay, don't be mad at me. Another example of a functor is the squaring functor. So we start again with a category, and for each object in the category we fix a product of the object with itself, A cross A, row 1, comma, row 2. Okay, so this evidently has to be a category that has these products. Okay. I want to define a functor C to C, and F of an object A is going to be the product, A cross A. Now what about morphisms? So we start with a morphism F from A to B. That has to lead to an image morphism A cross A, row 1, row 2, to B cross B. Say sigma 1, sigma 2, let's say, are the projections there. Well, this is another case for the mediating morphism trick. We're trying to define a map into a product B cross B. And as a matter of fact, if you draw the picture here, you will see that it looks almost the same as an earlier picture I drew. So I'm going to stop on this one as well and let you fill in the details. You can do this in more generality. The product, functor, that maps the product category C cross C into C. And here again we need to assume that binary products exist and that we've selected for every pair X and Y of objects, we select a product, fix a product, X cross Y, row 1, row 2. Okay. And so this functor is going to take an object in C cross C, which is an ordered pair of objects, to the chosen product. Okay. Morphisms are going to go to a product morphism, which is why I defined product morphisms for you earlier. And so I'm going to, again, leave that one for you to fill out. I now come to perhaps the most important example of a functor, at least from the perspective of category theory itself, the theory of categories. And these are the Homme functors. Again, we let C be a category, and A is an object in C. Let us recall that the Homme set, Homme AX, is a set of all morphisms from A to X. To define the covariant Homme functor, there's also a contravariant one. It's denoted by Homme A, comma, dot. And it maps the category C to the category of sets. So what does it do to an object? Homme A dot of X. You probably guessed it. It's Homme AX. It's this guy here. Okay. Objects go to Homme sets. How about a morphism? A morphism F from X to Y goes to the follow by F map. So if we complete this picture with a Homme set to Y, then here's our F. How do we turn a Homme set from A to X into a Homme set A to Y, followed by F? Homme A dot takes F to F back arrow. So F back arrow is mapping the image Homme AX to the image object Homme AY. And it's defined by F back arrow. Here's a morphism there, member of the Homme set. Tau is simply F circle tau. This is covariant because G circle F back arrow is G back arrow circle F back arrow. Okay. Following by G circle F is the same as first follow by F and then follow that by G. As I said, there's a contravariant version of this where we take Homme sets in the other direction from X to A, and so we will get Homme dot A. I will let you fill that in as well. Okay. So that's several examples of functors. I was a little less complete here than I have been in my previous lectures deliberately because I want you to fill in some of the details as good practice. Thanks again for watching, and don't forget to leave me comments. Thank you.